Assalamualaikum and good day. In this video, we're going to learn about chemical kinetics. There will be 7 separate videos for the 7 subtopics shown here. These are the lesson outline. At the end of this lesson, you should be able to define and determine the rate of reaction, explain the factors affecting rate of reaction, determine the rate law and order of reaction, apply Arrhenius equation for calculation of activation energy, relate between rate of reaction and temperature, predict the rate law from reaction mechanism, and finally, describe the two types of catalyst and catalysis. Chemical kinetics or reaction kinetics is the area of chemistry concerned with the speeds or rates at which a chemical reaction occurs. It is the study of the rate of chemical reactions. The word kinetic suggests movement or change. Once a reaction takes place, we'll keep wondering how fast does the reaction proceed? How far will the reaction go before it stops? There are many reasons for studying the rate of reaction. For a chemical reaction, the rate of reaction can be defined as a measure of the change in the concentration of a reactant or a product in a given time. Rate is equal to capital delta square bracket over delta T. The square bracket means concentration in mole per decimeter cube or mole per liter or molar. The usual unit for time is second. It can also be minute, hour, day, and even year. We know that any reaction can be represented by the general equation reactant to form products. This equation tells us that during the course of a reaction, reactants are consumed while products are formed. As a result, we can follow the progress of a reaction by monitoring either the decrease in concentration of the reactants or the increase in the concentration of the product. A shorter time reaction means higher rate of reaction, while longer time reaction means lower rate of reaction. This relationship shows us that the rate of reaction is inversely proportional to time. For a simple chemical reaction A to form B, in which A molecules are converted to B molecules, the rate of reaction is the decrease in reactant concentration A per unit time and the decrease of product concentration B per unit time. The decrease in the number of A molecules and the increase in the number of B molecules with time are shown in this figure. In general, it is more convenient to express the reaction rate in terms of the change in the concentration with time. Thus, for the reaction A to form B, we can express the rate as rate equals to negative sign of delta square bracket of A divided by delta T, or rate equals to delta square bracket B over delta T, where delta A and delta B are the changes in concentration molarity over a time period delta T. Because the concentration of A decreases during the time interval, delta A is a negative quantity. The rate of a reaction is a positive quantity, so a minus sign is needed in the rate expression to make the rate positive. On the other hand, the rate of product formation does not require a minus sign because delta B is a positive quantity. The concentration of B increases with time. These rates are average rate because they are averaged over a certain time period of delta T. Consider a general reaction. Reactants are to form product B. So from the tangent to the curve, we can write the rate of disappearance or rate of consumption of reactant R as rate equals to negative delta R over delta T, where the minus sign indicates that the concentration of R decreasing with time, and the rate of appearance or rate of formation of product P as rate equals to delta P over delta T. Let's consider the rate for this chemical reaction. Nitrogen monoxide plus half oxygen to form nitrogen dioxide. The rate of disappearance of nitrogen monoxide can be written as the rate of disappearance of oxygen the rate of appearance of nitrogen dioxide Our next step is to see how the rate of reaction is obtained experimentally. By definition, we know that to determine the rate of reaction, we have to monitor the concentration of the reactants or product as a function of time. For reaction in solution, the concentration of a species can often be measured by spectroscopic means. So if ions are involved, the change in concentration can also be detected by electrical conductance measurements. So reactions involving gases are most conveniently followed by pressure measurement. So we will consider these two specific reactions for which different methods are used to measure the reaction rates. This reaction of molecular bromine and formic acid. So in aqueous solution, molecular bromine react with formic acid as follows. Molecular bromine is reddish brown in color, so all the other species in the reactions are colorless. As the reaction progresses, the concentration of bromine steadily decreases and its color fades. So this loss of color and hence concentration can be monitored easily with spectrometer. So measuring the change in bromine concentration, which is decreasing at some initial time and then at some final time, enable us to determine the average rate of reaction during that interval. So the average rate can be written as negative delta square bracket of bromine over delta T, where it's the final concentration, subtract the initial concentration, divide by the difference in the time. So we can also calculate the instantaneous rate, where it is the rate for specific instant in time. So this plot of bromine concentration versus time based on the data shown in this table. So graphically, the instantaneous rate at 100 seconds after the start of the reaction, say, is given by the slope of the tangent to the curve at that instant. The instantaneous rate at any other time can be determined in a similar manner. So note that the instantaneous rate determined in this way will always have the same value for the same concentration of reactants, as long as the temperature is kept constant. We don't need to be concerned with what time interval to use unless otherwise stated. So we refer the instantaneous rate at a specific time merely as the rate at that time. For a graph of concentration versus time, the rate at any point can be measured by finding the gradient. So these two figures show the typical concentration time graph for reactants and product. The reaction at any particular time is given by the slope of the tangent drawn to the concentration time curve. Let's say this is the reactant concentration versus time graph. So let's see where you want to check the rate. Okay, so make a point here on the curve, right? And then just draw the tangent, okay, to the curve. And then as for the product concentration versus time, so we just make a point here, okay, and then just draw the straight line, okay, to mark the tangent to the curve. And then so the steeper the slope means the faster the rate of reaction. I would like you to go through this example where you have a reversible gas phase reaction between ethylene and ozone. So you are given a table that shows the concentration of ozone at various times during the first minute after introduce the ethylene gas. This figure shows the graph of concentration of ozone versus time during its reaction with ethylene. So let's see the corresponding line of A, B, C, D and E to the calculation of average rate and also instantaneous rate. Let's see if you want to calculate the average rate between 50 and 60 seconds. So line E will correspond to this calculation.